That's where we see a lot of new applications being conceptualized. Some of those applications absolutely need new materials. That's where, we come in, where we say that we can optimize a certain alloy according to what's required by that certain application or that.
Fazal, Phaseshift Technologies. I'm really interested in having you on because you're working on some really novel things. We haven't had anyone on talking about some of the more high-end STEM field kind of technology companies, like a technology company like yours. So you use AI prediction algorithms to develop material technologies. Is that correct?
Yes. Mm-hmm.
So what does that look like? Like how does predictions and algorithms work, and how does that translate into new materials, like physical objects?
Yeah, for sure. Well, I'm excited here to be as well. I'm always looking for opportunities to talk about my company, so this is this is a great opportunity for me as well. So as you asked, how can we use AI to sort of discover better materials? So I think before I answer that questions, I'll give you a short introduction of what phase shift is about, and that will hopefully lead into the answer that I want to give you. So phase shift essentially develops advanced alloys. So alloys, as many of your viewers might know, are a combination of a bunch of metals or metalloids. And once you mix those metals in a certain amount of quantities or certain proportion, they produce a specific set of properties. An example of which could be stainless steel, right? So regular steel is just iron and carbon because carbon prevents rusting. But once you add chromium to it, it becomes stainless, it becomes shiny. So just like that, you could mix a bunch of different metals in different proportions and you would get different set of properties. But the analogy I like to make here is cooking, right? Just like how you cook, you have a recipe you follow. Sometimes you are trying to come up with a new recipe. It might not work right away. It's more of a trial and error process where you try to mix a few things and you hope that the end result would hopefully be what you expect. Now, traditionally, the way any new alloy is developed is through trial and error, where a scientist would know that iron is strong. Adding carbon to it might reduce rusting. They have a specific knowledge related to each individual elements, and they would try to mix them in certain amounts to get those set of properties. Now, this doesn't always work because this is more of a guessing game where you would like just try something, and if you succeed, which rarely ever happens the first time, you end up wasting a lot of time and resources in trying to find the right recipe for that alloy. Now, where we come in is that we use AI to essentially predict those properties before we have created those alloys. So we have trained our AI models to essentially take in a composition, which is essentially, just elements and the proportion in that alloy. And once we give it that composition, it can tell us what kind of properties does it correspond to, right? So these could be properties such as mechanical properties, things like people might be interested in hardness, elasticity of the material, anything that could pertain to, like any sort of mechanical failure that can happen at certain point, things like that people might be interested in. Sometimes people are not interested in mechanical properties. They might be interested in chemical properties or electromagnetic properties. So we have different models that sort of correspond to different properties. Once we give it that composition, it tells us what kind of properties. So it saves us a lot of time and a lot of guessing work. But it's not sort of like a one-stop solution. It's not that we have to rely on the predictions. Predictions just help us see a bigger picture because we can apply this prediction modeling over a large range of materials, so thousands of compositions at once, which allows us to see a greater picture. We can identify sort of regions in the search space which would have the most interesting properties, and then from there onwards we do more intensive work. So to answer your question, that's how we use AI.
Yeah. I mean, you give us a. Sorry, I'm getting an echo here. Are you hearing an echo?
I'm not. If
Okay.
you are, I think it might be from my end.
Okay, no problem. So you give it a lot to digest, but one of the main things I want to take away from this is you're furthering the advancement, the ability to develop how materials like especially like iron and alloys are developed and created. And like one of my first thoughts into this, right? I remember watching like a TV show. I think it was like Avatar, like a cartoon show, and they were making a samurai sword. It's like a really epic episode. and they get the metals, but then they put like a bunch of stuff into it, like a coal to put the carbon and all these things, and it's like you're creating like a better metal out of the base material. And that, like, I remember thinking when I was younger, it's like oh, that's how things are made, right? And then and then in the show, like Rudimentary was talking about, like by choosing the different elements you're putting in here, you're changing the strength, durability, the bendability of the materials, and these alloys, by doing that, like by putting different elements in, you can change the composite structure of it, and through it change how the real world effects of them are after applied. So I guess, like, for most of human history, it's been, like you said, it's been guesswork, right? Like, you put different things in, you try to be as precise as possible, maybe when in a more industrial capacity, to get the most repeatable things in. But you hear about this all the time, right? Like, sometimes, materials come out of a factory. Some might deform, might not be as strong as the rest, right? Like, and when it comes, like, especially like building materials, it's so important to have them, calculated to be exactly similar, to be dependable, durable at a certain degree. But when it comes to that, like, we would assume, like, we as like a modern industrialized society, our material science has gotten to a point where, like, we have everything we need. We have glass buildings, we have skyscrapers that go miles into the air, like, that stretch into the atmosphere. Like, how much better can things get? So I guess the question is, right, like, yeah, even with this technology and things like that, like, what is the end game? Where does that lead to? What can come out of this?
Yeah, that's a very good question because it touches on a few different things here. Um, the primary question here is, where can we really apply this technology, right? You give examples such as, like, building materials, steel and things like that are used in construction, but that's not where we really see the value for these kind of technologies, right? So the market for just steel, iron and carbon, is quite large. Anything to do with iron alloys is a market in itself, let alone any other alloy systems. So iron alloys are, including steel, a very large market in itself, and there's a whole sort of field of study just around iron alloys, so steel and things like that, and there's a whole supply chain related to that, and the whole sort of chain is optimized around iron-based alloys. So the effect of that is that the cost of buying steel for construction or for other purposes is quite cheap, and it's much more difficult to replace an alloy like steel with something that is much more modern, because the chances of that new alloy being more costly than steel is a lot higher, because you would need to make changes in your processing and in your manufacturing process, things like that. So we don't see the adoption of technologies like these in industries where you're dealing with alloys that are used in larger quantities like steel or aluminum alloys or things like that, because it's harder to justify that even marginal increase in cost. So we don't really want to be targeting those areas as of now. Where we really see value is high performance areas, right? Like areas where you really absolutely need that marginal improvement in your material. High temperature applications where you need materials to exist in space for decades, or for space probes that are going into highly harsh environments like Jupiter's atmosphere or Saturn's atmosphere, so things like that. So their cost is not as big of a concern, because these are really bespoke applications. You're not going to be sending like hundreds of probes a year or something like that. It's more like a single probe will be sent to Jupiter, and that will operate for a few years. So where we really see value is these bespoke markets, where any marginal improvement in an alloy would mean that we're enabling a certain application for the client, or allowing them to do something that would previously not be possible. So we're talking about markets like the space market or the aerospace market. Even in aerospace, it's hard to justify a new material, because not only does it have to comply to a lot of like cost related constraints, but also you have to certify the material for use in aerospace. So there's a whole lengthy certification process. Then there's medical field as well, right? Medical field, the kind of alloys that we work with have most of their applications in the biomedical department, because of the kind of mechanical properties they have. There as well, you have to sort of certify the material for use within the body. So there's a lot of different areas. Cost is one of the biggest constraint for any new material because it's unlikely that you'll be using any existing processing techniques to create these new materials. It has to be bespoke to those alloys. So therefore, we don't see, any novel alloys that we create or any other company for that matter would replace an existing behemoth like steel or
Hmm.
aluminum alloys or things like that. But we do see an increasing rate of adoption of these kind of materials in industries that are growing, like additive manufacturing, right? Additive manufacturing is growing at a rate of 30% per year. The CAGR of that industry is 30%. That's where we see a lot of new applications being conceptualized. Some of those applications absolutely need new materials. That's where we come in, where we say that we can optimize a certain alloy according to what's required by that certain application or that process. That's where we see the market for these kind of technologies. But moving forward, even though some of those alloys like steel will exist for a while now, we do think that there's a whole new market of these bespoke alloys being created um, recently, because there's a lot of new companies that have come up in this area of materials discovery, especially in the space of alloys. So that's where we think the future is going, at least from our perspective.
Hmm.
Mhm.
Yeah, I mean,
Yeah, I mean,
talking about these
talking about this
bespoke
bespoke.
alloys, right? That's pretty interesting. So, what would the cadences look like? Would a company come to you and be like, "Hey, we need something that does this"? Like, do they give you metrics like we need this kind of durability, this kind of behavioral properties, this, or is it that you go ahead and you make like a variety of hypothetical products or situations in models, and then go out and find applications for them to market? Where do you start?
Yeah, I think both of those are right answers, because both of those are approaches that we are following right now. We do have projects where our clients gave us a list of properties that they wanted in their materials. That sort of is called the inverse design problem, because you have in a forward design problem, you have a material. From that material, you can get its set of properties by testing. But in an inverse design problem, you have those properties and you need to get the material from those properties. So that's some of the projects that we are working on, where our clients have given us those list of properties, and we are trying to find the compositions. In one of those projects, we have successfully identified some alloys as well that have improved performance over their counterparts. So we have demonstrated that this approach works. That material is in testing phase currently, so hopefully the results will comply with what we have tested, and they should, because we have tested a process as well. But there's also this other sort of approach that we have, which is also an approach that some of the other companies have taken, that they have, based on their own understanding of what the industry needs, they have created new alloys, and then they have sort of gone and found applications for those alloys. We have sort of taken a mix of both approaches, that we have these external projects where our client wants a specific material, but we also have these internal projects where we are developing our own materials according to what we think the industry needs.
Yeah. So I can definitely appreciate the challenge behind that, right? And the elements goes into determine that. What are the properties that a client will ask for? Like, how do you determine what are the property, what are the metrics they look for in a design material?
Yeah, I think, well, so far most of the properties have been related to, the material's mechanical nature and thermodynamic nature.
Hmm.
Just a quick overview of the kind of materials that we're working with. Generally, you have these traditional alloys that have a crystalline structure. So what that means is that the atoms in that alloy are arranged in a specific pattern. That specific pattern forms when you have a molten alloy, and when you cool it over time, the atoms in the melt just sort of arrange themselves in a pattern. Um, that pattern essentially determines how strong that material would be, and how would it behave under, like, extreme stress and things like that. So as you might have seen, like when they create swords in Japanese culture, they heat the sword, they cool it in water, they beat it. There's a lot of different cooling cycles that happen over time. That sort of gives it the alloy its atomic structure, the
Mm.
crystalline structure. But the issue with crystalline alloys is that the crystal structure is not perfect. The crystal structure has cracks in it, and those cracks, when they propagate throughout the material, they turn into faults, and that's where the material breaks. So hypothetically, if you could get rid of those cracks, those faults in the crystal lattice, you would improve the strength of the material by a significant amount. That's what we
Mm.
do. Our alloys are sort of built in a way that they don't have that crystal structure. They're a special kind of alloy called amorphous alloys. Amorphous essentially means random arrangement. What that means is that these materials tend to be harder, have more sort of strength. They fail at much more stress limits than traditional crystalline alloys. So for that, you need to control its thermodynamic properties much more closely than traditional alloys. So you need to cool it down really fast, at a certain cooling rate, all of those different things, or the atoms start to crystallize. So most of the properties that our clients are interested in are the mechanical properties and the thermodynamic nature of those materials. But that being said, these alloys also have very interesting sort of magnetic properties, right? One of the oldest applications of amorphous alloys is in the cores of transformers. So these electrical transformers that you see outside houses that regulate voltages,
Hmm.
um, the core of those transformers are made up of amorphous alloys that are based on iron, um, primarily because they have certain magnetic properties, and because of those magnetic properties, you have very low losses in current. So you can have a range of different properties, but so far we have seen more of an inclination toward mechanical and thermal.
Yeah. Do these
Mhm.
alloys, like we have like the main ones, like you said, like steel, aluminum, all that. Do they have names, like industry names, like, or is it scientific names? Like, how do they become categorized?
Yeah, you usually have sort of a naming pattern that's closer to serial numbers. You have
Hmm.
some letters and numbers. You know, there's a lot of different companies that have their portfolio of materials and they name it according to what they think is best. Um, in history, one of the older companies that have successfully commercialized amorphous alloys is called liquid metal.
Mm.
Liquid metal has sort of the word liquid metal has become synonymous with amorphous alloys just because they were one of the first few people to commercialize it at a larger scale. That's not to say that there's not other companies that have done it before them, but it's just that some things become synonymized with the product. So liquid metal is one of those. And they have their naming convention where they use the word vitrolloy, which has to do there's a word in chemistry that rhymes sort of that is synonymous with vitrolloy. So that's where they come in from. But different companies use different words and letters and numbers to identify that. But if you were to go and search for these kind of alloys, the words you would search for is amorphous alloys or bulk metallic glass or liquid metal. Those are all interchangeable for now.
Yeah. No, I mean,
Mhm.
so like this is like a very deep field into like a very niche category of developing these kind of things. What led you down the path of wanting to go here?
Yeah, it's a lot of different things that led me to this particular point. Um, as a lot of people who might be listening to this know that I don't particularly have a background in material science. I'm a
Hmm.
physicist. My co-founders are the ones that are, PhDs in material science, so they are the ones that are experts in this. But I'm a physicist. Once I graduated, I always had this inclination towards entrepreneurship. Um, this is just something that I've been interested in for a very long time since I was a child. My education has been in physics, and once I graduated, I joined this incubator at University of Toronto called Creative Destruction Lab.
Yeah.
Creative Destruction Lab is a deep tech incubator with a lot of different streams: space stream, AI, medicine, not medicine, health. Um, Quantum, and a lot of different deep tech areas. Once I joined Creative Destruction Lab, I really liked the space I was in and the kind of people I was among. So my inclination towards deep tech kind of grew. I
Mm.
always was inclined towards these deep scientific ideas because of my background in physics. Um, I never really liked that B2C space because I think I don't know much about that, and my understanding was more in the scientific areas. And I was also very fond of scientific computation, and I did a lot of courses in my undergraduate that made me really like this subject. So once I got accepted into Creative Destruction Lab, I was in the quantum stream, by the way. So I attended the quantum incubator program. Part of the reason we were part of the quantum program was because we do a lot of quantum chemistry. So a lot of the properties that we um, estimate from the composition, there's a lot of quantum chemistry calculations that go behind the scenes to estimate those properties. AI is just one part of it. 50% of it has to do with quantum chemistry simulations. So we are part of the quantum stream. And That's sort of like, once I was in the quantum stream, so you don't really apply with a business idea, you apply as an individual. And then you go through this 2 or 3 month long boot camp where they help you sort of conceptualize what you really want to, where you really want to apply your knowledge. I just really like the materials space, and I had a few different ideas at that point where I wanted to apply AI and quantum simulations to discover materials, but none of them were really, refined. Luckily, at that point, I connected with two professors at the University of Toronto. Both of them are in the material science department, and one of them is the supervisor of computational materials engineering lab. So they had a lot of expertise within this space. And I used to just sort of pitch ideas to them, and they would help me sort of refine this to a particular point. Um, and I finally sort of decided that, alloys is a space I understand at a high level, maybe not at a chemistry level, but at a high level. And I do see an opportunity because there's not a lot of companies that are doing this. This is a fairly unexplored space. But because of the fact that traditional alloys is already a pretty saturated market, and as I said, we are not going to go against something like steel or, an alloy that has been used for a while now. Um, I came across this sort of class of material that is called amorphous alloys, as I discussed. So that seemed like a really intriguing material class for me personally. Um, I have to admit that it seemed more intriguing to me before I even did my research, and I had decided that this is a space that I could potentially pursue. And once I started to do my research in sort of the market research and see if there's an opportunity for these kind of alloys, it seemed like there was this class of materials is just so underappreciated that there's a lot of space for improvement, and there's a lot of ideas that we can apply in this space. And that's when I sort of came across my co-founders as well, who were students in my this professor's lab. Both of them are currently doing their PhDs in this professor's lab in the computational materials engineering lab at U of T. And I pitched this idea to them. They liked the idea from the very first day, and we decided that we wanted to work together on the very first day. All three of us are Indian, so that helped too, because there was this ethnic I guess similarity, and we could really like talk about certain things the way we wanted to. So yeah, I came across this, and then we decided we want to pursue this. And since we were already part of Creative Destruction Lab, we had the sort of the support and the mentorship that was needed to start a company. This was my first time. Obviously, I don't really have a prior experience in entrepreneurship. I had worked with some startups before, but that was just more in a very limited capacity. This was the first time I was leading something, so I needed a lot of mentorship and a lot of advice from people who had that experience. So CDL at that point provided that. And the technical experience that I was lacking came from my co-founders. So there's a lot of like external help that I took, and I acknowledge that as well. So that sort of led me to a point where we, kept working on this idea, started pitching our ideas to investors, to clients, and slowly things started to fall in order. Like we got projects that we are working on right now. We did a successful fundraiser as well last summer. So the idea took some traction as well at that point. So it seemed to be, doing well. And it was more of a learning experience for us for the first time, but I'm glad that the learning experience was more so positive than, trial and error or something like that.
Definitely. That's definitely an interesting journey. Because most people who are into physics, they pursue like a PhD, and they try to they will go the professor stream and research stream, or they try to get hired by like Google or Intel and going into like those deep core research there in material science. But starting a company in such a space, I think it's inspiring because it requires a deep depth of knowledge in like the sciences and a very like very deep science, like you mentioned, but also that entrepreneurial capacity to take on risks and to bring on understand that the skill gaps and bring in people that can fill those skill gaps, find mentorship, and build those skills around just the research and capabilities of the hard science. So kudos on you. That's great.
Thank you.
I want to talk about, well, actually, I want to touch on one thing. So do you have a niche that you're going towards? I mean, I know like superconductor research, like materials for superconductor research is always been like one of the holy grails of material science. And you talk about space being like a space industry is popping up. I think 1/3 of the world's space startups are actually in India, right?
Mm-hmm.
And there's a huge boom right now in India in preparing for like micro robots and micro satellites and all these technologies coming up. Where do you see your lens of focus going moving towards, or are you seeing in general?
Yeah, it's a good question because this is something that we have discussed with a lot of people that we have fundraised from or pitched our company to, and we always get some mixed responses from people depending on what kind of background they have. Um, we have received advice that suggests that we focus on a single industry or a single application or a single niche market. But we have also received advice that suggests that we don't really focus on one industry because the market for amorphous alloys is pretty niche in itself. They have a very limited set of applications to begin with. So, and the capacity required to sort of work on materials that can be applied in different industries or different areas is not that much extra. Um, so we get all sorts of different advices. What we have personally chosen to do is not focus on a single niche. We have seen that other companies, are competitors that have worked on amorphous alloys or high performance alloys, they haven't really narrowed down to one single industry. They have a range of materials that they have produced or discovered or sell currently, and all of those materials sort of have applications in different industries. They have biomedical applications, they have applications in space. um, it's entirely possible that if you come up with a single material, it would find applications in different industries. It's unlikely that it would only be applied in one single industry. So we haven't really focused on one single industry because of that fact. That being said, one single biggest focus for us is additive manufacturing, so metal 3D printing. That's where we see the strongest pull for newer materials. So naturally, we are inclined to go towards that. And recently, there's also been a lot of studies that have been published, a lot of research that have come out, and they've demonstrated that for example, parts made out of amorphous alloys as compared to parts made out of traditional alloys, even nickel super alloys or titanium alloys, amorphous alloys tend to outperform those alloys, and a lot of those parts were created using 3D printing. So there's a lot of synergy between additive manufacturing and amorphous alloys. Part of the problem with amorphous alloys traditionally has been that they require high cooling rate. So because of that, you cannot create really large objects because they would have to dissipate heat really fast, and large objects do not do that efficiently. Um, so you could only create really thin rods or sheets of these alloys, but not really bulky objects. But with 3D printing, you're not really creating the entire structure at once. You have a bed of powders. You're only melting a very small subsection of the entire material, and it cools down sufficiently fast enough to inhibit any crystallization. So additive manufacturing in itself is unlocking a lot of applications using amorphous alloys. So they go hand in hand with this, which is why we are very much focused on amorphous additive manufacturing. And additive manufacturing in itself is not focused on a single industry. It has applications in many different industries. So that also sort of supports our argument that we don't want to focus on a single industry. But yeah, some of the applications you listed as such as microsatellites, that is one of the applications that we want to pursue in future using additive manufacturing. But yeah, we also always have to ensure that cost of those materials can justify the performance improvement, because these are expensive materials, and they have to have a justified performance improvement.
Yeah, I mean, it's interesting you brought out 3D printing. Like back in 2016, when 3D printing was like super in the mainstream and everyone's talking about it, the ability, the thought process behind like printing like metals seemed to be like oh my God, that's going to change everything. but then suddenly you saw like the slow decline of interest as like the the expectations were so high and the outputs became didn't meet up in time that the market kind of dipped again, and we see like 3D printing has kind of faded to the background where there's still applications for it, but a lot of it is in like in very niche categories. Where can what is the state of 3D printing metals, and where's that going towards right now?
Yeah, challenges with metal 3D printing are a lot harder to solve than challenges associated with 3D printing plastics. As you know, plastics, once you heat them, they become soft, and you could just extrude them through a nozzle and create structures, and they're a lot faster as well. With alloys, there's a whole other set of challenges because, as I mentioned earlier, the crystalline structure of the alloy or the atomic arrangement of the alloy depends on the cooling cycles that it goes through, the cooling rate it undergoes. So the cooling process of 3D printing, like the kind of process that you're using, such as laser melting or extrusion-based 3D printing, um, it's harder to control a lot of those different factors. So you have to control, what energy you're applying to a point, because if the alloy gets too heated up, it could, start sputtering everywhere. If it doesn't heat up enough, then it would not melt and solidify properly. So you have to control the process a lot more tightly than, polymer 3D printing. So it's been a more difficult space to operate in terms of like technical challenges. And but lucky for us, there's been a lot of different companies and a lot of different technologies that have done metal 3D printing. You have a certain technology where you have a bed of metal powder, so it's just really finely ground metal powder, and you have a laser that just sort of melts it in the right places and creates a structure out of it. This is a very slow process, so you won't be, creating a lot of different components from it, or really large objects or things like that. This is mostly used in the R&D space where you could like quickly prototype something and test it. Or you have this other set of technologies where you have just a wire made up of an alloy, and you just heat up the wire enough for the wire to melt or become soft, and then you create a structure out of it. But the structure from it is not as resolved or fine as the one with the metal powder. Where where amorphous alloys come in here is that, remember I mentioned that with plastics you can make the plastic softer and you could just sort of lay it wherever you want. Traditional alloys don't do that. Traditional alloys melting profile is different. You heat them to a point called liquidus temperature, and that's when they become fluid. That's when they become molten. With amorphous alloys, that's not the case. You have this region where they're not quite molten, but they're not quite solid. So they're soft. They flow like a plastic, but they're still solid, but they're still not liquid. So you can print them pretty much like you print plastics, but you're printing with metals. So that's sort of combining the best of both worlds, because you have the thermal profile you need to print plastics, but you have the mechanical properties of a metal. And that being said, alloys itself, amorphous alloys themselves, also have improved mechanical properties over traditional alloys. So we expect a performance improvement within the 3D printing space as well with amorphous alloys. In terms of the state of these kind of technologies, I wouldn't necessarily say that they have faded away, or the hype has died down. I think there's always some initial hype when there's a new technology that promises a lot, and that hype initially dies down. But I think the acceptance, or the adoption of this kind of technology has only increased. A lot of different industries are experimenting with 3D printing, whether if it is automotive, whether if it is aerospace, biomedical. A lot of different industries have started to work with 3D printers to create parts. Either these are really bespoke parts that are used in low volume production objects or products, or just in R&D labs where they want to just quickly print something and test it before they send it into production. So I would say 3D printing is quite a rapidly growing field. And as I mentioned earlier, if you look at the metrics for it as well, the cumulative annual growth rate of metal 3D printing is actually 30%, which is quite high for any industry.
So that's the rate of improvement right now, 30%?
Yes, so that's the number I have from last year. I'm assuming if it's probably gone up or gone down because of COVID, I'm not sure, but
Hmm.
that was the number I got last year. Yeah.
No, hopefully, man. Like usually, what I've seen is COVID has actually like, increased the improvement curve of a lot of technologies. 'Cause a lot more
Hmm.
money and a lot more financing has gone into developing different solutions, right? I mean, I think even like with the vaccines, one of the problems we have with the vaccines and development is not the actual vaccine itself, but the transportation. So the glass vials. There's only two companies in the world that makes medical grade glass. So the glass that doesn't fracture and particles of glass doesn't end up in the liquids, right?
Hmm.
Which for a vaccine you can see that being a
Yeah,
big
that could
case,
become a problem.
right? So the literally our choke supply in producing vaccines is not the actual vaccine, but the glass vials that are only made by two companies out of Germany, and they themselves have a problem with sourcing the materials, aka the right sand they need to like manufacture that. So materials and material science is so fundamental to a lot of the back end logistics in our world that we don't even realize. So I think what's going to happen is like there's definitely got to be more of a focus in the things that you do, and especially if you go into space, especially if you go into like superconducting space, if we go into like even like decentralizing the way we produce things instead of like having to ship things across the world all the time fully formed. If we can make things more locally, produce a infrastructure that allows us to do that, and I think materials science comes at the heart of that, right? Being able to develop things that can allow us to give that capability. Now, one thing I
Hmm.
want to do is take this conversation a little back, like into history. I'm not sure if you're a history buff yourself, but have you ever heard the term of wood steel or Damascus steel?
Yes, I have.
So yeah, so Europeans identified like Damascus steel, which came out of Damascus, out of like from the Silk Road, from the trade there, right? It came out of the Middle East, and in China, even with the samurai swords, sorry, in Japan, they were making these swords out of wood steel, which was wood steel and Damascus steel being a similar process of producing steel that were like in such superior supply than the existing steel that like everyone covered it. And any materials made out of this, especially like weapons like swords, vastly outperformed other weapons. They didn't rust as fast. They barely rusted. They last a long time. Were more durable. Stayed sharp longer. And it all came down to like the manufacturing of it. And crazy enough, recently people have traced the origins of both wood steel and Damascus steel, two separate ends of the world where it came from, and it actually originated in India, right? It came out of India, and this so like I've been doing a lot of research into the colonization of India and things like that. There was an MP out of Kerala that wrote a really
Shashi
great book.
Tharoor.
Yeah, yeah.
Yeah, he's
I
a
was listening to
pretty cool guy. Yeah.
Yeah, I love that guy. There was a period where I just like digested all his content online and all this because he systematically broke down like there's this world kind of belief that Europeans made India better, that colonization is improve life for India, whereas he brought up the evidence and showed us the exact opposite. And prior to the European colonization, like India existed as like a fallen civilization, where it's like manufacturing happened, but people don't know why it happened. Like the science behind it was lost, and people just inherited these skills from like past generations, and they're doing things without knowing why. And the supply chain was just there naturally. So one place in one township would perform, will do certain labor to like refine something a certain way, whether it be like wool or cotton or like metals, and then pass along to somebody else, and there's trade there, and then they take it on and do something else. But there's no overlistic picture of what was happening. So the Europeans saw this and as a way to disrupt everything, because the problem was after the trade with India was bankrupting Europe, right? And even
Hmm.
before that, the Roman Empire, when Rome conquered Egypt, and through Egypt got a supply route to India, through the Red Sea, into Africa and India, the entire like the Rome was suddenly experiencing a drainage of supply. All India wanted out of Europe was gold. Nothing else was important to them, like that was valuable. So gold kept leaving from the Roman Empire and even the British Empire. Gold was leaving out of Europe, out of the Western Hemisphere, and pouring it into India in return for not just spices but also these materials.
Hmm.
And it was bankrupt in the world. And that's one of the main reasons why colonization happened, right? It's because if it doesn't, it was like asymmetric trade patterns are developing. And one of the things that was heartbreakingly done was rather when colonization happened, it didn't happen by governments, it happened by corporations, right? East India Trading Company, the Dutch East India Trading Company, right? And these corporations realized, rather than absorbing the knowledge of the locals, right, and into them, like what it was doing was it was by buying superior products in India and sending it back home, it was disrupting the suppliers back home. And the native populations in their home countries were protesting this to the governments, and that could potentially end up them losing their license to operate the trade networks, right? So rather than learn the stuff, they purposely disrupted it. So there's all these cases where like there was raids carried out against these production villages where rather than they'll find these skilled tradesmen and cut off their hands so they can't perform their trade anymore. And they silence people who are teaching this, and it was systematically over 200 years reduce the capability of Indian of knowledge and capability, and it wasn't even trying to absorb the knowledge; it was to erase it, so that asymmetric trade would stop, just so the people back home would not the trade was not disrupting local manufacturing, right? And though inferior products, they became monopoly products, and they could be exported back out. Right, and the trade reversed routes over 200 after 200 years, and there was a wipeout of great knowledge loss there, and there's very little recording of it. But I know I was listening to a few things, and there was a few Indian professors talking about this. There are structures in India that still is documented from British India to now. I think there's in Chennai that's like a steel pillar, and documentation, like, it's shown that 500 years it's been standing there. It's made out of steel. No one has treated it or taken care of it. Like no extra
It's still not rusting.
But it hasn't rusted.
Yeah.
Right.
I think there's one like that in Delhi as well, either in Delhi or in Agra, but I've seen one myself. It's either made of steel or bronze or something like that, and it's still, if you look at it, there's no rust or any sort of like oxidation.
Yeah, like the Statue of Liberty, the Eiffel Tower, if left without consistent treatment from human intervention, if you leave it for like 60 years, it would erode away, right?
It's already green. It's not supposed to be green because it's made up of copper.
Exactly, right? And now and there's these structures in India, 500 years now, 300 years, documented proof. It's been standing there and it hasn't rusted. There has been swords been dug out of the ground, made out of this kind of process, and they haven't rusted, right? And it's like there's this lost kind of science behind things. And one of the interesting things about history, and as I've been learning and diving into it, we think of history as linear, right? We progressively just get better as a society, but it actually is ups and curves. And if you took a long look in history, it's actually, we're going up, but if you go back down enough, like it was like an inflection curve. There's a point where we have had knowledge and knowledges that were higher than what we could have now.
Like a breakthrough, basically.
Like the ancient civilizations were using technologies that we don't have right now, right? And we live among that, especially in a place as old as India. And you go to we look at like Egypt and the pyramids and all that stuff like as like, well, we can't create this now, like like the granite structures building the pyramids, we don't have the capability to build the pyramids ourselves. Even within the 600-year span it took to build that, we don't have that capability to do that. So it's like, at what point are we discovering new things, or are we rediscovering old things that we have lost?
Yeah, I think that's a very good. I mean, those are some things that I think about myself as well. There is this author that you might be heard. His name is Ray Dalio. Ray Dalio wrote one of his famous books is Principles. He's known for that book. He writes a lot about civilizations and politics and all of those things. And one of the things he argues is that, as you said, it's not a linear curve. It's not that we progressively just keep getting better, although it might seem so. It's more of a cycle. That's what he argues, that it's more like a cycle. And some of those knowledge, I guess, again, I think it's a mix of all of those things. I don't think it's just a complete cycle, or it's it's a linear, or it's a curve or something like that. It's a lot of different things that happen with different regions. Like in India itself was a civilization that was so much more different than every other civilization around the world. Like if you take Indus Valley civilization and compare it to like civilizations on the other end of the world, they would look completely different, right? Like they might have similar problems that they're trying to solve, but they would try to solve it differently. India itself went through, like Indian civilization went through a golden age. We have all these like different areas of study, like mathematics was a big thing in India.
Hmm.
You have Ayurveda, which is like, an Indian form of medicine, which is really popular in India, but it was conceptualized a long time ago. And while a lot of people might debate the efficacy of Ayurveda, like it still has shown to work in certain cases, right? It might not cure cancer, but it might cure some other illnesses that you might
Hmm.
be trying to work on. Um, so, but then India itself has gone through so many cycles of colonization. Um, I'm not exactly sure of the history of colonization like thousands of years ago. Like there's a lot of theories around like Aryan civilization that migrated to India. A lot of those things. I'm not very well versed on that, but from as far as I can remember, when India was sort of colonized by Mughal emperors, right, like Persian rulers, they brought a lot of their culture, right? Whenever
Hmm.
a civilization is colonized by another civilization, the the winning or like the overpowering civilization always tries to impose their way of life over the ones that they colonize, right? Not saying that that's justified, but that's an observation that people can easily make. Um, and whenever that happens, a lot of the information that was sort of conceptualized by the civilization that's being colonized is lost because of the fact that the new colonizing party won't necessarily accept their knowledge. They might have their own way of doing things, like they might have their own system of medication or own system of numbers. Um, then I think the biggest impact happened when India was colonized by, the British Empire, right? The corporations that came in, because that sort of really, if you look at the model of the government we have now, it's very much akin to the kind of model that they imposed on India through corporations, right? You have these taxes, you have licenses and stuff, the concept of licensing. Um, People not being allowed to do trade because it was disrupting trade patterns, monopolies and things like that, right? So
Hmm.
a lot of people wrongfully say that like Britishers came and colonized India and gave India so much like the rail network, but they forget that a lot of that is built on the resources that were taken away from India.
Hmm.
When a lot of gold was being taken from, as you said, like Europe and was coming to India, it was coming through trade. It wasn't being looted by Indian
Hmm.
rulers, right? It was coming through trade, but the gold that left India didn't left through trade. That left through by force, by colonization, by
Hmm.
ways that was not fair. Um, so a lot of that information as well left India, but wasn't really applied in the same way that it was intended. People look at Ayurvedic medicine and they laugh about it, quite frankly. Like they say that like our medical system uh, is built upon certain principles and that's why it's valid, while Ayurvedic medicine is not valid. I agree that the modern medicine system that we have works really well and is based on certain principles that I personally also agree with, but Ayurvedic medicine isn't simply invalid because the current system is better. It might have worked best at that time when we didn't have modern scientific equipments, the way of doing modern science. That's when Ayurvedic medicines worked. And if you look at material science as well, right, Damascus steel, or you're talking about these really strong materials that were used in warfare, right? That's back then nobody had resources to analyze the molecular structure of steel, or like what kind of material is being, what proportion of the alloy elements we have in that alloy, things like that. It
Hmm.
was only trial and error back then. That's still what we do, right? Even if we apply a lot of these technologies that we are building, it's still trial and error inherently, right? The predictions just do it faster than humans do, but it's still trying something and sort of checking whether if it's true or false. um, and a lot of those going back to like sort of the Damascus steel and like the way it was done, trial and error stuff, a lot of it had to do not with the composition of the alloy but also the processing of the alloy. People used to take a sheet of alloy, they would bend it, beat it, for hours, put it in the heat again, beat it again. What that does, it compacts the material into such a dense space that the material becomes really hard and really strong. Um, that's not a knowledge. Some of those knowledge is transferable, some of that knowledge is non-transferable. I think the knowledge that's non-transferable is the one that gets lost when it's you know if I tell you a piece of information, it's unlikely that 100% of that information will get conveyed to you. Now imagine that same concept but between different civilizations. Obviously, like, a lot of that knowledge will get lost, and I think that's where we reach a point where we have lost a lot of that inherent knowledge, and we're sort of working on it again. Um, that being said, I still think like there's a lot of new science that is being done. I don't think it completely comes back to that cycle. I think it's more of a spiral that's spiraling outwards, because now we have different ways of doing science. Now we can look at atomic structures of alloys. We can look at materials in a way that we haven't before, but it's still the same objectives that we are trying to fulfill, which is a stronger material that can, withstand certain set of conditions. I think I went to a few different places with that answer, but hopefully that
No, that
answers
was
on some of the
great.
things that you mentioned.
I had a professor who explained knowledge in a similar thing, just like you said, spiral that spirals out. You should imagine knowledge, our combined knowledge pool as a species, as like a sphere, it's a ball, right? And it's like there's a deeper core roots of knowledge that's like ingrained into all of us at the center, and newer knowledge is built outward, rated outwards. But like not all knowledge is equal. So like we put a lot of emphasis on the STEM fields, right? Like the math, sciences, the technology fields, right? So, and like, let's say materials technology, like, so in that area, that sphere, that it's mountains are there, like it's like a continent that rises out of the water. But in a certain, in like our current in our current understanding, in our current our culture, we don't put emphasis on like spiritual learning or like like or well-being knowledge or stuff like that. So there's like caverns that develop because they get outpaced by other knowledge that grows. And then there are peaks where like when like a PhD reads a thesis, or like a new thing comes out, it's like peaks within the continents of knowledge, right? And like slowly you're compiling knowledge on top of each other, packs and packs and packs and packs, until it becomes more ingrained into society, right? Like for now, like within the past 100 years, like the concept of DNA has been ingrained in all of us. Like almost every culture in this world understands that genes are inside of us, and they express how we are, and this is how it kind of moves. We have understanding, even though not a deep understanding, we know the idea of it. But 200 years ago, that never existed. That was new knowledge. That was that had to be compiled and then distributed into society and things like that. So knowledge kind of builds and compacts in each other. And what I'm interested in is like, how do we spread knowledge better, right? How do we get the right ideas out? Like, think about that as an entrepreneur yourself, right? Like when you want to acquire, you have this ability to create materials and build science, but like you then have to create a company, an entity, and then lead people, and then attract capital within a legal framework with accounting and taxes involved, and like grants and things you got to write. You got to acquire all these different skills and knowledge. You got to build around yourself that's contrary or vertical to the actual knowledge that you want to do to perform a certain task. So that's overly complications that happen within the innovation industry. And that's where a lot of people, founders fail. And that's why it takes them 2, 3, 4 companies in order to come up, because they can't pace themselves around, learning the right knowledge around what they want to do the task at hand, right? So I think there's going to be like the ability to be able to shift knowledge into people, right? It's going to be like a vector of leverage, right? I think Nabal Ravikant talks about this, right? Like knowledge being a unpermissioned leverage, like it's unpermissioned leverage. So like capital gives you leverage, technology gives you leverage, right? So if you as a human develop the ability to get knowledge or transfer knowledge, that's leverage you could deploy. And that's one of the reasons I love podcasting so much. Joe Rogan compares like YouTube to the Gutenberg printing press. So just like the printing press allowed the written word to be manufactured in like huge quantities at a lower cost of scale and be distributed, allowing knowledge to be distributed, like concepts like YouTube or like podcasts, audio, visual, right? Like look what we're doing right now. Like we're capturing all this, our ideas, thoughts, knowledge, but also with like our facial expressions and our movements and our tones and inflections, all that's captured, but in perpetuity that can be shared. Other people can listen in and like they can take off this. So I think we're seeing a radical transformation in the way we store and change and distribute knowledge. And one of the interesting things I think that's going to develop is cool. Now we have these stores of knowledge that can be stored all that. Like they talk about the next Google is going to be a database that AI or algorithms can tap into to better source things, right? So one of the things I think about too is like, how do we, just like deploy AI solutions to build like a better prediction of how materials could be. How can we source like AI or technology to better find things for us, to bring knowledge, to bring connections, to bring things to us?
Mm-hmm. I think that's a very involved question, and I think that's a question that I don't think will be very well answered anytime soon.
Mm-hmm.
Uh, but I guess the few things I'm thinking here is that how do you convey information, right? Like who do you think is a person who can convey knowledge better than someone else, right? Um, information is just essentially how you arrange different set of facts, right? You have very fundamental facts that you can arrange in certain ways that would give you sort of a piece of information, right? Just like in math, you can break down any mathematical operation into simple algebra, plus, minus, multiplication, and division. You could, and in two of those also you can do plus minus. You can take a piece of information, a fact, and you can break it down in a way that's understandable to anyone, right? If I mean, I'm talking about alloys and material systems and crystallization and all of these different things. But if I had an infinite amount of time, I could break it down in a way where I could explain it just using balls and squares and all of those different things, right? And it would make perfect sense.
Mm-hmm.
It's just the constraint of time that allows us to abstract that knowledge in a way that only a particular set of people can understand that, because you're using all of these different terms, these abstractions that not everyone will understand.
Mm-hmm.
So I think this abstraction is what essentially allows us to build that superficial knowledge on that sphere, right? If you think of globe and you like an onion, you're adding an individual layer of knowledge
Mm-hmm.
every set amount of time. If we don't use that abstraction, we won't be able to build that knowledge on the surface, because then you're considering all the knowledge that's under it to explain that just a little bit. So we need that abstraction first. Um, and then like, how do we find the right knowledge, right? Like you're talking about like YouTube and all of these different things that sort of serve as an archive of knowledge, right? It's just essentially a huge library on internet of videos. uh, Entities like Google are essentially doing that, right? They're building an archive of information, and as you may know, information is one of the most valuable resources in today's time, even more so than oil, I would argue. um, so information is a very heavy, or like very expensive commodity at this time. So how do we sort of find the right piece of information, or like convey the right piece of information in this pool of information that we have?
Mm-hmm.
I think that's difficult, because having all of that information, while it's great for humanity, it also sort of crowds the space, right? If you're trying to find a piece of information, it's unlikely that you will find that exact piece of information that you're looking for, but you always find supporting facts or information around it in that sort of space. Um, Now, where sort of this interesting way of thinking comes is that you don't look for that explanation. You have your own explanation that you justify using a set of facts, right? You have this model of hypothesizing something, creating a model, and then testing that hypothesis or that model, right? That's something that we do in astrophysics. So I one of my majors in undergrad was astrophysics as well. And you don't really go and test a lot of different things in space, right? You just look at observations and you make models and you try to justify those observations based on those models. Sometimes those models work for a long time, sometimes they don't.
Mm-hmm.
That happens with physics as well. Newtonian physics worked for the longest time. Then we had quantum physics that explained a lot of things that Newtonian didn't. Some things work at different times, some things don't. Um, so to find the right knowledge or piece of information that you're looking for, I think it's important to conceptualize the question that you want to ask. I think it's very important to know what you're asking first. And once you have the right question in mind, you can very easily create a model of to sort of, test that question or find the right piece of information. And then you can sort of go and search for supporting facts that justify your hypotheses. That's one way to find information in this very crowded space, especially internet. When you talk about internet, you have pretty much everything you want on internet. I don't think I had a question ever in my mind that I went on internet for and I didn't find an answer.
Hmm.
There's always something, but it's never a perfect hit. It's always sort of supporting facts. So even subconsciously, we are always trying to create these hypotheses and testing them on internet because it's unlikely we would ever find that exact same question.
Yeah.
Um, but that sort of like again touches on some of the things that you mentioned. I think it's hard to answer what you asked because it's a very abstracted question in the first place,
Yeah, yeah.
and
It
it's
wasn't so
more of
much
a
as a
philosophical question.
yeah, it wasn't so
Yeah,
much as a question as like a ask, right? Like a philosophical
yeah, yeah.
ask.
It's more philosophical. Yeah.
Yeah, but I mean, going back to that, like I think Ray Kurzweil, the founder of Singularity University, he talked about this, right? Like AI fully realized will
Hmm.
allow us to test and deploy things at the speed of thought. So we have an idea and work with an AI to like deploy it. Whether it be an abstraction, like like as a prediction, or like even like get things made right away, right? And there's obvious power in it. But what does that mean for your field as technology gets better and computing gets better? I know you doubled in quantum computing with your with what you're doing, right? As computing gets better, as power gets better, as its algorithms get better, what does it allow you to do in your field?
Yeah, I think there's two things there. As computation itself gets better, the power to process data, and that's what essentially we're looking for in quantum computing as well, because the kind of improvement that we're expecting with quantum computing is just unimaginable with classical computation. Like you could have a single quantum computer with 40 or 50 logical qubits that are, we're assuming that these are perfect qubits that have no error in them, or like they work ideally as we expect them to. They could have the computation resource of, uh, I guess, all the supercomputers combined on this globe. That's maybe more than that. So
Mm,
it's unimaginable what you're looking for in this. So you can process the amount of data that we have all over the globe and like come up with predictions, or try to make estimations, or try to do whatever you want to do with that data, in a way that it was never possible with classical computation. Things that would take decades to compute could be computed in a matter of minutes with quantum computing. So the future for data processing is quite bright, um, and that enables a lot of very exciting things, especially in the field of AI, where you have a lot of data processing. You could process data in a way, or create really complex models that would take a very long time to train and make highly accurate predictions, right?
mhm,
One of the problems with AI is not the amount of data that we process, but how do we make AI as general as possible, right? Human mind is the most generalizable AI that there is, right? We can do so many different kinds of things. AI is just more specialized in one thing. So what we see is that AI will sort of become like what cyborgs are. Cyborgs essentially aid your human body to do, really unimaginable things.
mhm,
So with AI, what you can do is you can, they will aid you to do certain things that your natural human mind cannot do very well, right?
mhm,
Um, Obviously, you cannot just look at a set of atoms and predict its properties, right? But AI can.
mhm,
You can do certain things with AI that human body can't, but we don't see that as a threat to what human beings can do right now. Human beings
mhm,
are the one that are creating the AI, right? So
mhm,
what AI will do is help us unlock certain areas or certain applications or certain processes that humans were just not capable of doing. It will just sort of act as a helping hand, in terms of like, in different areas, whether if it is discovering better materials, natural language processing, identifying objects from images. Those are very general areas. But in my particular field, if we had an AI that's just, as best as it can get, and we have quantum computers that can process all the data, it would mean that we could predict material properties with a level of accuracy, or just simulate their behavior in a way that it's just not possible right now.
Mm-hmm.
Because when we run certain simulations, right, we essentially what we do is we recreate that alloy virtually. We have a box of 200 atoms or 1,000 atoms or 10,000 atoms. We heat it to a certain temperature, cool it down just as we would in real life, and we see what kind of effects we have based on certain calculations. But those calculations, one, are really slow. It takes sometimes 2 days, 3 days, 4 days to complete a single calculation, or they have some inherent error associated with them. So what that allows us, if all of those challenges were not there, we could just predict the future in a way that if we just add these elements together, what are the exact set of properties we need. We still rely on experimentation to verify our predictions, but with those things we might not even need to experimentally verify those things. We might just have a set of calculations that could go directly into productions. But that's pretty far ahead in future. Experimentation is still the gold standard of verifying a lot of these claims.
Mm-hmm.
So I think that will stay like that for a very long time. But until but once quantum computers become, more commercializable, or if we have more computing power, or if we have better AI, that could unlock a lot of different things that we want to be able to do at this stage, but are just not possible.
Cool.
Cool.
Awesome.
Awesome.
Fazal, man, it's been an hour. I really enjoyed this conversation.
Me too.
Really enjoyed having you on. Thank you so much for your time. And for everyone who tuned in, thanks for watching. We're going to end this episode here, but stick around. We'll do a quick debrief.
Thanks for having me as well.